describe some of the features that we see in the CMB from first principles. We're making very many approximations, recall, so we're getting only a crude picture. To do everything, you really need to solve this stuff numerically. But the idea is to sort of see how new physics might imprint itself on these features that we are describing here. So we're doing learning enough physics about the process to see how new physics might change the shape of the CMB power spectrum when we calculate it from first principles. Okay? And so I've already come in here and written down our master equation for the evolution of fluctuations when modes re-enter the horizon and we have the photons, electrons, and baryons oscillating as sound waves, which then, as they oscillate, they are caught at different times in their oscillation at the moment of recombination, which we saw last time led to these peaks separated by L of about 200. Okay, so that's where we left off. And we had assumed in that calculation that the baryon fraction relative to the amount of photons that we have in the fluid is vanishingly small, so heavily radiation dominated. And in that case, and also there's no anisotropic stress in that case. Phi over here is equal to psi. And in that case, this equation simplified dramatically to a nice, simple wave equation. So you just got sines and cosines. Matching on to initial conditions gave us a transfer function that showed that the evolution of a scale invariant set of initial conditions evolves into a set of peaks. Okay? So now what we want to do is start diving in and taking into account some of the other effects that we know are going on, such as a non-vanishing baryon to photon ratio. Okay? So let's turn on a little bit of an R in this case. Question, yes?
Sorry, could you turn on the lights, please?
Where are somebody else who knows where the lights are should turn them on. Okay. Sure. And so what we can do is turn on.
Is that okay? Too much light? Yeah. Oh, it's fine.
Now they stay awake. The light is really bright.
Now we have a radiation background.
Sorry? Yes. We are now well, not maybe radiation dominated, but we've changed the ratio. So now let's take R not equal to 0. And again, we're making a crude approximation. Let's just say R is not equal to 0, but it's a constant. It's going to be evolving as a function of time as the ratio of matter and radiation changes as the universe evolves. But we can go ahead and just set it equal to a constant to get a rough idea of what a non-vanishing baryon fraction leads to. So if you do this and you plug into this equation and take a small value of this ratio, you can first, you find that there is a small amount of anisotropic stress, and that the difference between phi and psi is proportional to this ratio R. And when you now take this equation and work in this limit, the equation is no longer a usual wave equation, but one in which the oscillations occur relative to a different equilibrium point for the oscillator. Okay, so now in the presence of a gravitational fluctuation phi, theta now oscillates about a different midpoint. And so now remember that the transfer function that we calculated, the way that it appears in the CLs is as a square. And where here we have the initial conditions set by whatever the dynamics of inflation were. And when we square the transfer function, which has in it, that's an upside down W, TSW squared is going to have a contribution that is theta squared divided by that initial condition, oh sorry, just theta, no, squared because I squared everything, okay, good. And so this means that because the midpoint has shifted for different peaks, we draw just sort of an oscillation here, here's the unshifted oscillation, and now we have a shifted oscillation with a different 0 point. When we square this thing, the alternating even and odd peaks are going to have different heights, okay? And this is indeed what we see when we look at, say, the first couple of peaks. The second peak is dramatically suppressed compared to the first peak, all right? And so now this gets us some idea of what's going on at this epoch where matter starts to be a non-trivial component of the fluid. The ratio of the first and second peaks are going to encode information about that fraction of baryons to photons. So the relative height of those first two peaks gives us information about how much baryons are in the fluid at the time. Okay? So this is how we can gain access to interesting physics that's happening between the time when a mode comes into the horizon and when it exits the horizon. It gives us an idea of what is the physics between the mode entering the horizon, and here's all of the physics encoded in the different elements that are appearing in the master equation. And then there is the surface of last scattering. And we recall that the equation for the evolution that encodes the Sachs-Wolf and the integrated Sachs-Wolf, that the leading term only depends on the fluctuations evaluated at that surface of last scattering. Okay? And so the physics is encoded up there through this transfer function. Okay. And now there are, this is one effect. This is referred to as baryon loading. Loading because essentially you're adding more of a massive particle to the system, and that thing will carry, inertia as it wiggles back and forth, and so it kind of adds a loading term to the fluid. That it's an extra cost for creating oscillations. Another interesting effect is, whoop, where'd it go? Ah, there it is. Okay, is called radiation driving. And this is a bit of a subtle effect, and it involves something that we won't solve here. But the idea is that when modes are entering the horizon during a period of radiation domination, there is a very quick fall-off of the metric fluctuation components of the entire physics of the oscillation. Okay? And so that's, you see this in the picture up here where'd my, oh, there it is. Where phi here is dropping like a stone as a function of time. And what happens is you start off with a rather small amplitude for the oscillation at first. this phi kind of gives the thing a push, right? But then that phi is gone, and it's no longer sort of pulling back on the fluctuation here. So it gives it a big push, but then it goes away. So there's sort of like a kick to the fluid from that perturbation phi. OK, and then the thing just oscillates with a higher amplitude than you initially started with. And so what this does is it gives a enhancement to some of these peaks relative to what goes on later. So this increases a bit the heights of these peaks around here that are entering in that period of radiation domination. Okay. So phi sort of drives an oscillation and then lets it go. Just like sort of whacking an oscillator, yes, and then letting it move about. OK. And another aspect of what was shown in that same plot is a damping effect, this sigma term here. And we talked about this, actually, I referred to this briefly in the discussion that we were having yesterday. And this is a manifestation of the phenomenon of cutoff, right? If I've got a lattice of atoms and I try to wiggle that lattice of atoms such that I would be creating wavelengths that are shorter than the spacing between those atoms, then I'm not going to get any bang for how many bucks I put in to the oscillation, yes? And there's an analog in the photon baryon fluid in that there is a mean free path for the photons as they're making their way through the plasma here. And so what is that mean free path? Lambda gamma, so what are the photons banging into? They're mainly banging into the electrons via Thomson scattering. And the Thomson scattering cross-section is nice, or sorry, the mean free path can be expressed nicely in terms of the Thomson scattering cross-section as the following, okay? Where this is the number density of electrons, and this is the cross-section, all right? And so now what this means is that oscillations are going to be damped whenever the wavelength is smaller than this sort of characteristic length scale for the photon baryon fluid. So what is the damping scale? So the photons are banging around in the fluid, and they're undergoing a random walk while in the fluid. And we know how to calculate how far something moves in a random walk of n steps. Okay? And so what we can do is we can calculate a damping length that is going to be the number of steps taken by the photon times that mean free path for the photon in the fluid. So now, what is n, right? We need to get an idea for how many random walk steps does the thing take, which is going to correspond to a region on the sky over which those photons just sort of mix hot and cold spots, right? So they damp the coherent stuff that would lead to structure on smaller scales, right? And so this is going to be the square root of a time scale divided by lambda gamma times lambda gamma, or root tau times lambda gamma. Let's write that below. Okay. So now we can take into account the contributions of this damping scale on the transfer function, right? So there's going to be an additional term that damps oscillations whose wavelengths are smaller than this damping scale. This is lambda, this one here, lambda gamma. It shows up twice, right? So we have lambda gamma here. The number of steps taken is going to be the time scale that the photon gets to wander, which is going to be basically the time of last scattering, t star.
So it should be.
Oh, sorry. Yes. Very good. I just didn't complete the square root. Okay, thank you. So now we have a transfer function that, because of this additional effect, is going to get sort of a damping coefficient, which will depend on the wave number times the original transfer function that we calculate ignoring this effect. And this damping term is exponential. So from this characteristic damping scale, we can calculate a characteristic k. And so for a wave number k, we get this additional effect times whatever the original transfer function was, ignoring it. Okay? And so this effect is going to influence primarily the modes with short wavelengths. Modes with short wavelengths are going to get a larger contribution from this damping, and shorter wavelengths, at that time that we freeze them onto the sky, at that time of last scattering, is going to correspond to the higher multiples, those things that are measuring primarily correlations at small angular distances. And so again, we look at this picture and we start to understand why everything is falling like a stone on the right side of this line. Okay? So now we've got a rough picture of what's going on from this point here down until here. So here is that damped region. Here is the region where we see oscillations caught at peaks. We get a relative height due to the baryon loading. And we have some basic idea of what's going on in this picture now. Now, interestingly, if I look in region 1, this is the case where modes are entering the horizon right around the time of recombination. And this means that they don't even get a chance to start oscillating before recombination happens. So there, the transfer function is going to be trivial, right? No physics happened. The thing entered right here instead of over here. And so we get a projection onto the CMB of only the initial conditions. So at low multiples, we really are seeing the modes that, yes, were frozen, and they never got a chance to unfreeze before we get our picture of the sky in the CMB. Okay? So questions about this? This is a little bit probably where I was aiming at finishing yesterday. But it actually turned out that I think this is it was a nice way to start this lecture, because we're actually going to talk a lot about these features and how they're affected by the presence of some physics beyond the standard model in this intervening epoch between when the mode enters and exits. Questions? Yes?
Professor, can you comment about the phi behaviors, like why it falls like that?
I actually don't have a good understanding of actually why it falls off. I know that there's a GR calculation that you do that causes that rapid fall off in phi. So there's a, yes, so you just calculate the behavior of Einstein's equations in a radiation-dominated epoch. And what pops out of that is this decaying phi. I'm sorry I don't have a better answer for you. I'm learning this almost as I go because this is not my main focus of research. But you can go into Daniel Bauman's book where he does have a specific detailed calculation of how that occurs. Yeah, sure. Okay. Any other questions? All right. So now what I want to do is talk about, as I said, the effect of new physics on the picture that we've painted so far. And we don't have an entire semester. Let's focus on one example that people like to play with are things like dark radiation or maybe very light pseudo-Goldstone bosons, gravitinos, things like this that are part of many interesting models that we like to play with. So we want to know how tight is the straitjacket for playing with those models, and what would be their signature in the CMB, and how soon will experimental data kill your favorite model, okay? So these are the things we want to figure out now. So whenever I say I've got some new light massless particle, we might expect that if there's some coupling to the standard model, and the question we might ask is, was this particle ever in thermal equilibrium with the standard model? I always use this symbol for equilibrium, because equilibrium is long to write, and I probably spelled it wrong. So for example, dark radiation whether it be a gauge boson or a light scalar field, is going to contribute to something that we call N effective. So if it has energy density rho x, then what we can do is we can calculate a ratio between rho x and some other relativistic species that we expect to be around, like a neutrino density. And so we define delta N effective when we introduce a new type of radiation as the ratio between the energy density in that species and the energy density in say, a single neutrino species, all right? Just one of the three neutrino species. So if you like, N effective counts the number of neutrinos roughly, right? So if I wasn't looking at just the delta, and I added up all the neutrinos in the numerator, I'd get roughly 3, okay? Not exactly 3 for reasons I'll mention coming up, but just in passing. We can write this in terms of a quantity that is more sort of manifest when we look about, and that's the density of gammas, where this is just a numerical factor, which if you write it out, has to do with the relative fraction of the energy density between neutrinos and photons, which is the inverse of that 7/8 that appears in calculating the number of degrees of freedom, and that 4/11 that shows up when we calculate the relative temperature between the neutrinos and the photons post-injection of the decay products of E plus E minus annihilation. And it's raised to the 4/3. And then we've got rho x over rho gamma. Okay? So these are just different ways of writing this. And this is just definitional. We call delta N effective this ratio just because we did. We decided to do it that way. Now we have constraints on N effective because the number of relativistic degrees of freedom affects the Hubble rate. And remember, the Hubble rate is that figure of merit that we compare our reaction rates to figure out when things decouple, okay? So during radiation domination, this is easy to see. We just have h squared is 1 over m Planck squared times the total energy in radiation. It's the 3. And when you add this up, it's going to be 1 over 3m Planck squared, and then your pi squared over 30 g star, the effective number of relativistic degrees of freedom, times the temperature to the 4th. Okay, so for a given temperature, if I change the number of relativistic degrees of freedom, and effective is inside this g star, then it'll affect the Hubble rate. Okay. So what are the values of N effective that we measure by looking at nucleosynthesis and getting, say, the right amount of helium, things like this? So this is from the CMB, and we'll talk a bit about why the CMB constrains N effective. And there's also strong constraints from BBN. Okay. So this is kind of our wiggle room and playground currently for adding new relativistic species that were in thermal equilibrium. Okay, so just like we calculated the relative temperature of neutrinos and photons, we can do the same calculation, again, and this is an important assumption, making the assumption that entropy is conserved throughout. This is how we got this fraction of neutrino and photon temperatures. If we use entropy conservation, what we find is that the temperature of a species X as a fraction of the neutrino temperature is the number of degrees of freedom at the temperature at which the neutrinos decouple. So Td is decouple, nu is this is the decoupling temperature for the neutrinos, divided by G star temperature of decoupling of our new guy, x, we get the same power of 1/3, where we get the 4 over there because it's temperature to the 4th, yes? The 4/3, times T nu, okay? So now we have an idea of the fraction. If we know the fraction of temperatures, we know the fraction of how this contributes to N effective, okay? Now we write this in the following maybe funny-looking way. So we can calculate this. This is 2 photons plus 7/8 times the electron densities. So we can just stick in the numbers for this, and we get 10.75. And then we stick something in both the numerator and the denominator. Because this is an important reference number. And now we have our unknown, T decoupling for x. And I ran out of space, so I'll actually just write the ratio over here. So this is Tx over T nu, okay? Now 106.75 is the number of relativistic degrees of freedom in the entire standard model if you go to very high temperatures. And so it's just convenient to have that as kind of a reference figure, because the time of decoupling of this new guy, x, might be at very high temperatures when everything in the standard model is highly relativistic. Maybe this decoupling temperature is 10 to the 10 GeV or something like this. So then you've really got to add up all of the degrees of freedom, okay? And so then we can then write this as Tx over T nu is equal to, okay, we just crunch the numbers in there. We get 0.465 times that 106.75 over G star Tx, T decoupling for x, to the 1/3. Okay, and so this now gives us our N effective just by plugging it into this formula and raising this guy to the 4th power, okay? And the idea is that after this point, the x's and the neutrinos don't get any injection into their energy like the photons do from the E plus E minus annihilation. So this ratio just holds constant when other stuff is injecting energy into the plasma, okay? So this is just a nice steady figure of merit that you can use, which is part of what explains why this is the way we define delta N effective. All right. And as we'll talk about in the next bit of time, there are constraints on delta N effective from CMB data and from Big Bang nucleosynthesis, all right? And the current constraints are that 2 sigma bound right there. And so these different lines correspond to different cool physics models that might produce these kinds of light relics that would contribute to N effective. And along the bottom line, we are varying the decoupling temperature of that new species, okay? So maybe just a quick question for the audience. What is this feature right here? Why is this changing at this point? Anybody? why is there this feature, a little bump, right around this particular very interesting temperature? So what's going on at that point? Yes, the electroweak phase transition. And what happens at the electroweak phase transition? We give masses to a bunch of the standard model particles, and at that point, the number of degrees of freedom at the time of decoupling is going to change by, so the top quark goes away, the Higgs goes away, right? And so you can count the number of things that go away, subtract them from this 106.75, and you get a feature. And there's a big, huge one right here at around 100 MeV for a similar reason. There's a QCD crossover, at which point all of the quarks and gluons go on to form baryons and mesons, all of which have masses. And so you get a very steep fall off at that point because you lose a lot of relativistic degrees of freedom in the process of going through that crossover. Okay? So that explains these features. And if you like, it puts a limit on the scale of decoupling for these different cool physics models. Yes? And what is super interesting is that if we are able to build the experiments that we'd like to build, we may gain an enormous amount on the limits on delta N effective. Okay? And so we'll spend some of the time either today or maybe in the beginning of lecture tomorrow, depending on where things go, seeing why that is or how that is. Okay. Good. Yes?
So the experimental limit, the current limit, shouldn't it be temperature dependent?
So the limit just puts a limit on delta N effective. There's maybe a bit of temperature dependence because there's only a couple of temperatures involved. There's the temperature of Big Bang nucleosynthesis and the temperature near recombination. So there's only a couple of moments when we get that constraint on an effective. So it's really only those couple of temperatures where we get strong information about it, right? They're so close together, I guess, that we don't bother making two different plots. But I guess, yeah. So this is somehow a combined limit, taking into account both of these things. I guess you could make two different plots doing just this, and maybe they would look slightly different. Maybe that's the answer to your question. I'm not 100% sure, but okay. And the reason there's different numbers for these different species is that each of these species themselves carries a different number of degrees of freedom internally. So a Goldstone boson is spin 0, just has a single degree of freedom. Weyl fermion is spin 1/2, so I'll get up-down, so I'll have 2 degrees of freedom. And a gauge boson has the 2 polarizations. No, sorry, Weyl fermion has 7/4 because of the 7/8 factor. 2 times 7/8, excuse me. Okay. So now let's talk about how delta N effective affects the CMB. The first way that it affects it is through an increase in the amount of this phenomenon that we talked about a little while ago, is this diffusion damping. And the way that we get excess diffusion damping is, let's consider a ratio between the damping scale as projected onto the angular sky. Okay? There's a theta damping, and this again corresponds to this mean free path of the photons, divided by theta star, which again is that characteristic L that separates the different peaks in the CMB. Okay, that L of about 200 corresponds to a theta star of about 2 degrees or something like this, if I remember right. We wrote this down in terms of a sound horizon distance, which is just the speed of light times the time scale for sound to travel, which is t star, times the speed of sound times the time at recombination. Okay, and KD is just the characteristic K for when you start to get diffusion damping. Now, we're not allowed to change this because it's measured very, very precisely. We just look at the peaks and we see how far apart they are, yes? This is less known. It depends on the angular distance, which in turn depends on the evolution of the universe from recombination to now, which involves things that are less known, like the amount of dark energy and things like this. Okay, so we can now express this in terms of changes in these things that leave this fixed. KD involved a square root of the travel of the photon, yes? And now if I include the Hubble rate in that, that's going to change the distance that it goes. And so you get a square root of the Hubble rate here. And the sound distance, sound horizon, is going to have an inverse factor of Hubble. So we get Hubble at recombination divided by the square root of Hubble at recombination, giving us an overall square root of Hubble at recombination. So now this means that theta d is going to increase with an effective if I have increased the Hubble rate due to adding some new relativistic degrees of freedom. And so this is going to change the tails of the CMB and give more damping than you would have predicted otherwise without the presence of this new species. And so here in the top left is a plot of that. So actually, plugging in this contribution, this excess diffusion damping, which, if you look up there, as you increase n effective, is causing a quicker fall off at high L than a smaller n effective. Question?
Yeah, we're missing some dimensional factors then, right?
Oh, proportional to, sorry, yes. So I'm just power counting the Hubbles. All right. Unfortunately, there's a little bit of a degeneracy between this effect and another effect. And that is, because this is affecting BBN, it's going to change the fraction of helium-4. So effectively, what's happening is, remember how we calculated the helium-4 fraction? We had competing Boltzmann tails between the neutron and the proton, and we got a rough factor of 1/6 in the fraction between those. But that depends on the Hubble rate, right? And so if this helium fraction changes due to that different number of relativistic degrees of freedom during the time of BBN, it's going to change the number density of electrons present at the time of recombination. Why? A helium-4 likes electrons more than hydrogen. And so this means that before recombination, if there's more helium nuclei around, they're going to steal the electrons before they recombine to the hydrogens. All right? And so these two effects sort of cancel each other out, it turns out. And so just by looking at this, you can't tell if it's an effective or some slight modification of what's going on during BBN. Happily, it turns out there's a more subtle and interesting physics effect called the phase shift between where you would expect the peaks to show up and where they actually do show up. And so that's what we'll just display briefly, or talk about briefly now. Of course, I erased the master equation. I won't rewrite the master equation, but I'll just say that if you consider the epoch of radiation domination and you're a bit more careful about the way that you take the r equal to 0 limit, then you get, well, first let's write down the r equal to 0 limit, taking no difference between psi and phi. So taking into account anisotropic stress. So we have delta gamma double dot minus CS squared, del squared, delta gamma is equal to 4/3 del squared phi plus 4 psi double dot. And now we're going to, just like we rearranged to write the equation in terms of this theta, assuming that phi and psi were equal to each other, instead we'll consider a different combination, d gamma, which is 3/4 delta gamma minus 3 psi. Okay? By the way, there's a typo in, I'm 99% certain there's a typo in Bauman's lectures. He was referring to a paper by Selyak and Baczynski, who used the opposite conventions for phi and psi. And so this is the way you get the next equation that I'm writing down. I wasn't able to reproduce it otherwise. And it's that d gamma double dot, just plugging this in and rearranging, minus CS squared del squared d gamma is equal to del squared of phi plus psi. Okay? And just call this phi plus. Okay? So it's just a different way to rearrange this equation without necessarily making assumptions about the metric perturbations. They're all over here. And so now you've got an oscillator with kind of a driving term. And the solution can be written as, for a single Fourier mode, and let's use because it's showing up everywhere, CS k tau. We define y as CS k tau. So we have this of y is equal to some coefficient a that we match to initial conditions, cosine of y, and then minus 1 minus 3, 1 over the sound speed squared, we're in radiation domination, integral over dy prime of this combination phi plus, okay, times the sine of y minus y prime. So we get this extra term in the solution that we didn't have before. Okay. And we can expand this out using trig. I won't do it. We'll just write things in terms of a nice couple of parameters, alpha and beta. These are functions of y, okay? The alpha is a function of y. Minus 3 beta, and these all actually should have k indices. And so this overall thing is clearly periodic, but it's not just cosines. They're relatively periodic up to the y dependence of these alphas and betas, okay? So now, but y has to be evaluated eventually at the surface of last scattering. So what are these alphas and betas? They're integrals, the remnants of this integral, where alpha k is roughly the integral over phi plus k times the sine of y, and beta k is the integral over phi plus k of cosine. All right? And now if you just rearrange this into one oscillating function, what you find, as long as there isn't a lot of oscillatory dependence in alpha and beta, that the solution can be written as d gamma k.
What are the boundaries of this first integral?
Ah, yes, 0 to y. Good, thank you. Yep. And so then eventually this needs to be, right, so this is y. We're integrating over y prime, and we're integrating up to the surface of last scattering to get the transfer function. Okay, so now the solution is just a single cosine, similar to when we got theta before, yes, times, but with an additional phase factor, where our phase factor is the ratio of beta divided by square root of beta squared plus alpha plus cs squared a squared. A squared. Good. Okay, so now what we see is that there's a non-trivial phase factor as long as beta is not 0, okay? And now the next step, you'll have to just take on faith that beta is only non-zero when there's a contribution from a relativistic species. Neutrinos actually give this phase factor, and it's my understanding that this phase factor has just recently been observed, although not constrained. It doesn't give a strong constraint on the number of relativistic degrees of freedom. And so this phase factor shows up in this picture here, where if you kind of zoom in on these different sort of flattened out pictures of the CMB, ignoring the damping, okay, so you factor out the damping, you see that there's a slight phase shift if you zoom in, okay? As you vary n effective, the phase, where the peaks show up in L varies by a little bit. And so n effective does two things. it shifts the tail, but that's degenerate with the helium fraction. But it also shifts the phase, which does not have this degeneracy. So now we can pin down N effective without having this sort of flat direction in the fit along with the helium-4 abundance. OK, so that's the quick picture of what's going on. The integral over this is actually kind of interesting. You take this thing into the complex plane, and the thing is 0 when you do the sort of contour at infinity, unless the speed of the guy is the speed of light, which then gives a non-trivial contribution. So it seems like a sort of tour de force calculation by Selyak and Baczynski. OK, so what time do I stop? 12. I have 30 minutes. Oh, fantastic. That looks great. No, it's fine. I think it's good. OK, so the main point here is that the physics of light degrees of freedom imprint themselves upon the CMB, and that we can then use the CMB to constrain these light degrees of freedom. And so this picture here is just of a bunch of planned improvements on getting better and better data on the cosmic microwave background radiation. I don't think the time scale is right. I don't know when exactly this plot was made. They're always made very optimistically. So smear out the years on the bottom or add a length dilation feature or something to get the right answer. But the idea is that on the time scale of our careers, maybe even mine still, we might actually be constraining this delta N effective so that we could really rule out a lot of pictures here. You'd really be getting down with future sensitivity to very high decoupling scales of these degrees of freedom. Okay? So you have access to very high scales. Cosmology is giving you access to physics that you wouldn't be able to access otherwise. OK. So now I want to talk about new physics. Other questions on this before I go on? Yeah.
Could you maybe explain again why the change of the helium-4 fraction also causes like a damping in the tail of the CMB?
Right. So remember, there's a Doppler contribution to the CMB, and that Doppler contribution is going to depend on how many electrons there are around at the time and what the Hubble rate was at the time. And so I think that's what the effect is. So if I'm depleting the number density of electrons, then I'm changing the Hubble rate and the physics at the time of last scattering. And so that then gives a small effect in the CMB.
So the whole chain would be the new particles change like the ratio of protons to neutrons. It changes the rate of the helium.
Which changes the electron number density. Yes, that's exactly. Very good.
And it would be more helium gives you less electron, so less Doppler.
Because if you
I want to be careful. I'm not super sure that that's the right way that it goes. It sounds plausible, but I don't want to say I know what I don't know.
because I think that when we are starting radiation in the medium, we're gonna have washout of matter. So maybe the electrons cut off from the atoms, and it will avoid, for example, the formation of helium.
So the helium is made. The helium well, the helium nuclei are made. It's just a question of, once the helium are made, they're going to poach electrons from, the would-be surface of last scattering, right?
Yes, but then with more radiation in the medium, we cannot have these electron bonds. So the radiation will wash out.
Yeah. Yeah.
So the fraction of helium will increase.
Yeah, again, I don't want to confirm. I just want to say there's an effect from it. There's clearly something that's going on because I changed the helium fraction, and it is degenerate with this effect. So I'll just leave it there. or maybe turn it on over to one of the organizers if they, the leaders of the school, if they know the answer. Question, yeah.
So in the delta degrees of freedom, the curves that are shown, these are other models, like the variations of the...
Sorry, just give me 1 sec while I turn off this stupid thing. I can't find my mouse, though. It's probably because this thing is here. And this thinks it's my mouse. Sorry. OK. Sorry, ask one more time.
The plot, the figure with the variation of degrees of freedom.
This one here?
Yeah. So this goes to the different curves or models that alter the
Yes, yes. So each of those is a different type of new physics. And I'm going to give you a laundry list of cool new physics ideas that would give them.
Yeah, but any curve that goes out of the current limit,
Yeah, so I can't go bigger than that limit. So some of...
Anything that goes above it would be discarded.
Yes, so we are just... not if it ever goes above, right? So there's a decoupling temperature. And so if the decoupling temperature is above, 100 MeV or so, around the time of the QCD crossover, then there are no longer any constraints past that point.
All right, so the current limit is only up to how much?
Yes,
temperature?
right.
To which one?
Around the QCD crossover, it looks like about 100 MeV, from the picture here. Yep. And that's not very far away, right? 100 MeV decoupling temperature. That thing's been in thermal equilibrium all the way, until the QCD phase transition. So it's a fairly weak bound currently, but it will get super strong because of the way these things kind of flatten out because of the, it's really the QCD number of degrees of freedom drop that gives this effect, because there's so many, quarks and gluons that are lost in the bath at the time of the QCD crossover. Okay, so new physics. The idea here is not to give a complete model, but rather to write down an effective theory that plausibly incorporates new particles like the ones that are on this picture. And the way that we talk about new physics in the absence of the complete big picture is in terms of an effective field theory, where when I write down the Lagrangian for the physics that's going on, I only write down the operators that are allowed by the content and the symmetries. And so you can schematically write this down as our effective theory that incorporates some new physics X will be written as the Lagrangian of the standard model sector plus maybe a standalone Lagrangian for the new physics sector. Maybe it's just a kinetic term or something like this. Or maybe a kinetic plus potential term. Plus a sum over operators that mix the new sector, the new physics, and the standard model. But again, that where these terms remain consistent with the symmetries of the theory. Okay, so it's kind of a simplified model. We're ignoring where these particles came from up to the symmetries that they manifest that sort of keeps them light and in the picture. Okay, you say light massless particles. We've got a spin zero particle. Csaba has been telling you about how we're not supposed to have fundamental spin zero particles, but there are workarounds with that. If there is some kind of symmetry protecting that massless particle like a continuous symmetry that was spontaneously broken and has produced a light Goldstone boson. Okay, so they've been careful in this plot to only write down light particles that are light because there's a reason for them to be light, not just because I say they're light. Okay, so consistent with the symmetries that protect them. And for simplicity, for our discussion, we will just maintain that there's only one new light particle at a time. If you want to go home and put more light particles, you can do that. But for the purposes of our discussion, we'll consider one at a time, as is done in that plot up there. And plausibility is that there's a symmetry protecting it. Okay, so what about spin 0?
Can I ask a question to that plot?
Maybe, sure.
Probably a very stupid
You can certainly ask the question.
There's the standard model line missing, right? So, I mean, do I understand correctly? In the standard model, delta N effective would be 0
Yes.
at very large temperature. So there should be a dotted line or whatever with the same shape below those colored curves, right? Because also without no physics, delta N effective changes as the temperature drops.
Sorry, I don't quite follow. So the standard model line is just there's no change in N effective. I guess at some point you're taking this decoupling temperature out to implausible values. Yes.
The structures are because standard model particles disappear from the spectrum.
Yes.
But that also happens without no physics. Or am I not understanding correctly?
It's at certain time.
So you're saying that there is definitely a new light particle there, right? In this picture, there's definitely a new light particle, and so the standard model line is just 0 all along the bottom, right? Because then there's no species X. This is the decoupling temperature of the species X. So to put the standard model on here doesn't really make sense because it's just delta N effective is 0 because there's nothing decoupling. Does that answer it? Yeah. Okay.
Sorry, but my question was the same because then any curve that goes above the current limit is discarded.
Right, so you discard that model that has a decoupling temperature, which will depend on its interactions, right? This decoupling temperature is going to depend on these, right? These are the things that are, in principle, keeping that new species in thermal equilibrium with the standard model, right? So there's a couple of presumptions here. This thing was in thermal equilibrium with the standard model at some point in time. So that went into this plot. If I discard that, then you have more freedom. So this is not saying that if I have this thing, then this is absolutely, killed. It's saying that if I have this species and it was in thermal equilibrium and there was no injection of entropy at various times, then this is the line you get. If you want to have another model that breaks those assumptions, these lines will change.
But it looks like it's delta N at 3 equal 10 to the 6, so the relative difference to the number of degrees of freedom at the beginning,
Yeah, maybe we discuss after, or maybe.
I mean, you have to read this plot as you choose a temperature of decoupling for your model, and then you can read off what is the corresponding
Limit,
change.
or the corresponding delta N effective, yeah.
But the T that no.
Is good? Okay. Okay, so spin 0 are scalars, and if they're going to be light, the things that can protect spin 0 scalars are that they're realizing some continuous symmetry nonlinearly, that there's some kind of shift symmetry at low energies. And they are massless if the symmetry is exact. And maybe there's some small breaking of this symmetry. which yields to m not equal to 0. But this small breaking, if this thing is a Goldstone boson, will have calculable effects on the potential. And as long as those breaking effects are small, then the mass induced is going to be small. You can sort of parametrically calculate this mass as sort of an epsilon, which parametrizes the amount of breaking of the symmetry, explicit breaking of the symmetry, times some breaking scale at which the symmetry breaking took place, the original spontaneous symmetry breaking. Okay? So parametrically, it looks like this. And so here you would have a light pseudo-Goldstone boson, which we write as PNGB. Okay? Now, what are some interesting examples of spin zero Goldstone bosons? Axions, one of which perhaps is responsible for solving the strong CP problem associated with the QCD sector. And here you have a broken Peccei-Quinn symmetry. My favorite example that I like to play with a lot in research are dilatons. And here, the symmetry that is spontaneously broken is a space-time symmetry. It's conformal invariance. And then there are other examples like familons if you have some spontaneously broken family symmetry, or meyerons if you spontaneously break some lepton symmetry. There are lots of interesting ideas for fixing problems with the standard model that have as a consequence light particles that arise due to the spontaneous breaking of those symmetries that solve those problems. Now these different models will have different characteristic coupling strengths appearing in these operators mixing these two sectors, okay? The standard model and the new particle sector. Oop. Here's where I ran out of an entire book. So the axion example we'll spend a bit more time with. And so I'll just lay out a little bit more the kind of interactions that arise in axion models. Again, this axion perhaps solves the strong CP problem, and it does so by promoting the QCD theta angle to a dynamical field. And there is a potential induced by non-perturbative effects in QCD where the axion rolls down to the minimum of this potential induced by non-perturbative effects, and the effective theta angle at the minimum of this potential, if the only thing giving rise to this potential for the axion is QCD, is equal to 0. And so this is a really nice, compelling picture, and it motivates considering these axions as light particles that are around today. And maybe they make up the dark matter too. So what are their characteristic interactions with standard model fields? There are others, but I will focus mainly on L axion. Contains in it terms like -1/4, and let's write this as 1 over lambda q, axion F dual. So this is a field strength F mu nu. This is a dual field strength F mu nu. And this thing is basically the field strength squared, but contracted with the epsilon tensor instead of the metric tensor. Okay? Plus 1 where this potential actually comes from. Let's call it 1 over lambda 3, axion GG dual. Okay? Now there are other interactions with fermions, but let's just leave this here as it's going to be the one that we are most able to constrain with data potentially. Okay, well, with data, and even better with improved sensitivity in CMB. So I think I just, rather than writing out the interactions and all these, let's just make a list of the different spin possibilities. So here we have a Weyl fermion or a Dirac fermion. And let's say the symmetry that protects it is the chiral symmetry associated with introducing fermions. Okay, and now once you dictate that that's the symmetries, that tells you what the allowed operators you can write down consistent with those symmetries. Things like antipole couplings to the antipole moment and couplings to the dipole moment. Spin 1. If it's massless, we know it's protected by a gauge symmetry. Or if it's broken, well, you have to explain why the mass is so small, the thing that Higgsed it, right? So let's just consider a massless spin 1 field. Otherwise, we've introduced the hierarchy problem for the thing that gives rise to the mass for the spin 1 field. So we are trying to stay within plausibility and naturalness. Why is this thing there? So there's spin 3 halves. And here we start to get into sort of rarefied models that produce them. This is quite generic. This is pretty generic. This is pretty generic. We don't have as many places to get a light spin 3 halves particle, but the spontaneous breaking of supersymmetry in a mixture of SUSY applied to a theory with gravity, or SUGRA, supergravity, produces a gravitino when supersymmetry is broken, where the mass of the gravitino is suppressed. So we have a SUSY breaking scale, and we have the Planck scale. And its interactions are suppressed not by the Planck scale like the graviton is, but instead by the SUSY breaking scale. Okay, so they're not suppressed by some super big scale, but by some low scale, so they can in principle be in thermal equilibrium at some point. Spin 2, we've got even more rarefied. There's nothing that you can do to get other massless spin 2 particles besides have diffeomorphism invariance. You're very limited in what you can do. So the only thing for spin 2 is the actual graviton. And we know how that couples. It's super, super weakly coupled. It's never going to be in thermal equilibrium with a standard model. And so we can kind of cross this off for consideration on a plot like this. OK, so now what we want to do is come up with a way to figure out where does my model fit on this, a plot like this one going forward. Let's see. OK, so I'm not going to do this yet. I'll just leave it up there. The figure of merit on the horizontal axis for that plot was the decoupling temperature. So what we want to do is figure out what are the decoupling temperatures as a function of the parameters of the model, those g's that appear in the effective theory that I write down. What is T decoupling for X? Okay. So what do we do to calculate a decoupling temperature? What we need to do is work out the interaction rate which is going to depend on those couplings between the standard model and this new species, right? And we want to compare this to the Hubble rate at different epochs in the expansion of the universe. And we know that when these two cross, the solution to the Boltzmann equation is going to throw this process out of balance, and we will lose equilibrium between this species and the standard model. The thing will freeze out. Okay? So what is the interaction rate in, say, the Axion model? So let's focus in just on this one. In the Axion model, we can calculate the interaction rate as a function of these two lambdas, lambda q and lambda 3. Let's just say lambda I, and temperature. And so I'll just write down, using naive power counting, what the answer is got to be. We know we're calculating an amplitude using these things. So we're going to get 2 powers of these lambdas in the denominator. There'll be some pi factors, all this stuff. Let's incorporate those in terms of prefix gamma. So we have a gamma q. In principle, this thing depends a little bit on temperature, but this is a dimensionless quantity that we're putting in here. And T is the only thing it can depend on. Yes, there's no other scale in the problem. That's setting the energy scales for everything. And if we've got 2 lambdas in the denominator and we want this to work out to a rate, then we've got to have a T cubed in the numerator. Okay? Yeah, I wrote a sum, but I'm just adding the 2 together. Okay. Gamma 3 of T over lambda 3 squared T cubed. Okay? So these gammas are just some coefficients that will depend on actually calculating these rates and working out the factors of pi. But they're dimensionless, so they should only logarithmically depend on T. Maybe there's some running at different scales that will cause these to change slowly. So if we're in an epoch of radiation domination, as we will be for most of the interesting spots on this plot, then we know how H scales with T. And so we know as the universe decreases in temperature that eventually this rate will cross the Hubble rate. Okay? So now what we can do is we can place bounds on the decoupling temperature when we set the rate here equal to the Hubble rate. So we need this fact right here, right? The reaction rate needs to be less than the Hubble rate in order not to have these things in thermal equilibrium, right? We want to avoid thermal equilibrium so we don't end up on this plot. Okay, so sorry, I'm throwing myself off. We need the interaction rate at the reheat temperature So we're producing these things early in the universe. There is inflation, there is reheating, and it's during reheating that we populate everything. And if we have the reheat temperature below the decoupling temperature, then we avoid these species being in thermal equilibrium, and we don't end up on this plot whatsoever. So the idea that we're looking at is we're going to probe way, way down on this plot with future experiments, and so let's come up with a way that we stay off this plot altogether. And do not get any constraints. So this is like what are the models that will survive after we improve significantly the constraints on an effective?
But more excitingly, we will see something.
Of course. So what is the part of the parameter space that will observe? Yes? Okay. Yeah, so this reheating temperature is not on this picture right here. So there's a decoupling temperature, and what we're trying to do is make it so that, let's imagine that the future sensitivity goes all the way below this thing, so that you would, if these things were there and they were in thermal equilibrium at some point, then they would be ruled out, okay? And the reheating temperature, if the reheat temperature is below the decoupling temperature, then the species will never be in thermal equilibrium. It won't be there. So this does not give any constraints. Yeah, sorry I tripped over myself a little bit here, and I think I'm back on track now. Okay, so from this, we have gamma as a function of temperature, and it's not hard to calculate Hubble as a function of temperature. We just say that gamma is less than h, but in terms of things we know, like the relationship between the energy density in radiation here, we know this in terms of the relativistic number of degrees of freedom, and so this will be square root of pi squared, the total number of degrees of freedom at the time of reheating. We have a factor of 90, which was the 3 times 30 that showed up in this. And we have T reheat squared divided by m Planck. Okay? So now we have gamma, we have h, and we can now get a constraint equation that says that, let's say I turn only one of these on at a time just for simplicity. And it tells me that lambda I must be greater than pi squared over 90, the number of relativistic degrees of freedom at the time of reheating to the minus 1/4, and then the square root of that calculable gamma factor for I at the time of reheating times m Planck times the temperature at reheating. Okay? Good. So now we can get a constraint on these lambda i's. They've got to be bigger than some number. So for axions, we can get constraints from looking at different observables like stellar cooling. So as a star is cooling, it'll emit axions if there are axions in the game. And from limits on stellar cooling, we can put a bound on the lambda q on the vertical axis versus the mass of the axion, which is so we get some constraints in this plot. And so there are things like ADMX, which is an experiment looking for dark matter axions, which is probing the lowest down, but presumes we have a dark matter component. So if you take the figures of merit for the Axion model that we've been considering, and you plug it into these n-effective constraints, where this 0.027 was sort of the very, very lowest that you could get delta n-effective if the thing was ever in thermal equilibrium, we can rule out all the way down to a much, much higher lambda gamma that we were able to probe before. And in fact, we're getting deep into probing one of the most interesting Axion models, or the spectrum of Axion models, those that solve the strong CP problem. Okay? And it is not dependent on axions actually being the dark matter, unlike the ADMX experiment there. Okay? So you get sort of more model-independent constraint on the presence of these axions as a light new degree of freedom. Okay, and I'm out of time at this point. I'll just flash that you get a similar constraint from the QCD coupling. So this was looking at lambda q. You can also look at lambda 3. You previously get constraints from contributions to the neutron electric dipole moment. Now we could additionally get constraints from much improved observations of the CMB. Orders of magnitude improvement on things like supernova constraints, potentially. It depends on the temperature of decoupling, though, as we have on the side of that slide there, that plot. Okay, and so other interesting relativistic scenarios are left as an exercise for the student. That was the parting word of Daniel at the end of this section in his notes. Okay. So, other questions? Yep. Yeah, actually, could you bring up the microphone? I can't quite hear you, sorry.
Yeah, so you shown a plot where axion decay constant is compared with the mass. Yeah, in
Yes.
this plot. So we can see there is a little window left by ADMX experiment. So what is the region that unconstrained region in between two bounded region is left by ADMX?
So everything kind of under these lines is allowed once you have sort of the very best of the best of CMB experiments. Is that what you're asking, or?
No. So ADMX left little window between two.
Oh, the gap between these? I don't know, actually. Do you know?
I think it's just, it's broadband, it's narrow band cavity search, I think, and there's a gap between.
I couldn't hear.
I think they want to look at the, they skip because they want to look at the string network, that is 10 to minus 6 something, and they skip some because it's not as interesting.
So they were able to just adjust the experiment to start to probe a region of axion masses, that's right?
ADMX is good.
Yes.
And so at some point they decided to skip some frequencies because they weren't as interesting.
They're driving down to the QCD axion band. So their focus is on getting down as far as possible. And then they change the experiment and then move to a different frequency.
But they haven't yet, so they did this first and then they were able to get down here, you're saying? I see, yeah, okay. Good. Was that your question? Is that good?
Okay, so just a reminder that at 2 o'clock, there's a colloquium by John Turning in this room where we'll also be joined by the workshop participants for the new perspectives on particle physics, but let's thank Jay again.